The enthalpy change, the energy change during a reaction. For exothermic reactions, reactants have high energy and the product is having low energy, and the enthalpy change will be negative. Where for the endothermic reactions, reactants have low energy, product is having high energy, and the enthalpy change will be positive. Then standard enthalpy change of formation means when elements form a compound. Combustion means when 1 mole of a fuel is burned under standard condition. And what are these standard conditions? The standard conditions, we have 1 atm or 100,000 Pascal, 298 Kelvin or room temperature 25 degrees centigrade, a concentration of 1 mole per dm cube, and substance have their normal state at 298. Neutralization, enthalpy change of neutralization means when 1 mole of a water is formed by reaction between acid and alkali. And atomization means energy required to produce 1 mole of a gaseous atom. We call that as standard enthalpy change of atomization. According to Hess law, the overall energy change is independent of the route or the path which we follow. So how we identify the start of the cycle, where the two arrows are pointing out, that's start of the cycle, and the two arrows are pointing in, that's end of the cycle. So if we follow A, the route 1, or we follow route 2, the overall energy change will be same. So using this law, we can find the enthalpy change for different chemical changes. It can be used to find enthalpy of hydration, energy change when water is added to anhydrous salt, or it can be used to find enthalpy change of decomposition. If in the question enthalpy change of formation is given, so which link you will add? You will add elements. And the cycle which you will make, element can form reactant, reactant form a product, or element directly form the product. Or if combustion is given, so you will write the combustion product for both. You will write the combustion product for both reactant and product. The combine, and the arrow should point, like you burn reactant, you get the combustion product. You burn product, you will get the combustion product. So arrow will point in. This is the thing which we discussed in the last session, and did some examples. How we can find enthalpy change using a calorimeter method. So what we will do for a reaction, if it is it occur in aqueous medium, or if a reaction is exothermic, it will release energy. So we can find the amount of energy absorbed by the water, and our assumption is that the energy released during a reaction is same as amount of energy absorbed by the water. And to calculate the energy absorbed by the water, the formula is Cm delta T. M is the mass of the water, actually the mass of solution or mass of water, because we assume that the density is 1 gram per centimeter cube. So if we have like 30 cm cube of water, we will have 30 grams of, or 30 cm cube of solution, it means we have 30 grams of water will be there. And the specific heat is 4.18. The temperature change, we'll multiply them, we'll get the energy during this change. This is what we discussed in the last session. Now, more examples related to enthalpy change. Finding the enthalpy change of combustion using a calorimeter. Like if you want to find how much energy is used or how much energy is released when we burn a substance, that is known as combustion. And if we want to find the enthalpy change of combustion, so what we will do, we'll take a spirit burner which is filled with a fuel which we are burning. So when we burn this fuel, it will release heat energy. And what we will do, we will take a calorimeter. It can be made up of copper. It can be made, normally coffee cup calorimeter, different material can be made, but it should be a conducting material so that it can transfer the heat energy to the water. So we have a water inside. The volume of the water which we will take in a calorimeter, that is same as the mass of the water. Like example, if I took 20 cm cube of water, It means I have 20 grams of water. We will, using a thermometer, we will record the initial temperature. So by using a thermometer, we'll record the initial temperature, and when we burn this fuel, we will record the final temperature. So using the change in the initial and the final temperature, we will find the change in the temperature. And how much energy absorbed by this water, we can use the formula E is equals to Cm delta T, or Q is equals to, so specific heat is 4.18, M is the mass of the water which we will measure, and delta T is the temperature change, so we'll know how much energy is released. But to get the enthalpy change, because the term enthalpy change means energy release per mole. So we are burning the fuel, so energy divided by mole. So from mass of the fuel, we can get the mole of the fuel, and energy divided by moles of the fuel, we will get enthalpy change for combustion. So example, calculate the enthalpy change of a for a reaction for which 0.65 grams of propane 1-ol completely burned and used to heat up 150 grams of water from 20.1 degrees centigrade to 45.1. So we have the mass of the water. The mass of the water is there. That's 150. We have the specific heat constant 4.18, and delta T is a change in temperature, so which is 45.5 minus 20.1. We'll get the energy. Then, because we need enthalpy, the term enthalpy means energy per mole. As we are burning the fuel, so we should know the moles of the fuel. The mass of the fuel is given 0.65, so moles equal mass in gram divided by molar mass. Mass in gram is 0.65, molar mass is 60. When we divide, we'll get the moles. And energy divided by number of moles, we'll get energy per mole. But the answer should be in kilojoule, so we'll divide by 1000, we'll get in kilojoule per mole. And because this is an exothermic reaction, as the temperature increases, so 1 mark is for mentioning the negative sign. So as the last, the final answer should be minus 1470 kilojoule per mole. Is it clear, this example? How we work out the energy change per mole for exothermic reaction in which we burn the fuel. The energy which is released during a combustion is absorbed by the water, and that energy is used to change the temperature of the water. Using a temperature change, we'll find how much energy absorbed by the water, and energy divided by moles of the fuel, we'll get energy per mole, which is also known as enthalpy change of this reaction. Like how much energy, when 1 mole of a fuel is burned, how much energy will be released. Is it clear? Then what are the errors in this method? What are the things which can lead to a wrong result? Because what is happening, like we have a calorimeter which is filled with water, and we are having a burner, or the spirit burner is there, in which we have fuel. When we burn, it release energy, and that energy is absorbed by the water, and it show a change in temperature. So the problem here, heat loss from calorimeter, because maybe what happened, calorimeter absorbed heat energy, but it's not transferring all of its energy to the water. Some of the energy lost to surrounding. Incomplete combustion of the fuel. If this fuel is not burned completely, because complete combustion release more energy as compared to incomplete. Our assumption is that the fuel burned completely, but in practical, maybe it will produce unburned carbon, or a black soot is formed. So due to this black soot or unburned carbon, it means the temperature will not rise to a higher value what it should rise. Incomplete heat transfer. Basically what happened when we are burning, so some of the heat energy is transferred to the surrounding. Evaporation of the fuel after weighing, because as we took in the previous example, we were having a 0.65 grams of propane 1 all. But maybe because these are volatile liquids, so some of the fuel might evaporate. So as the fuel might evaporate, we will not have the same 0.65 gram of a fuel for combustion. We'll have less than that. Then heat capacity of a calorie, because what we did not include, it's not like all the energy will be transferred to water. Calorimeter will also absorb some energy and it will show a change in temperature, but that we did not include. Measurements not carried out under standard condition, like if we don't have the standard condition, we have different surrounding temperature, not 25. So the enthalpy change will not be a standard enthalpy change. And measurement not carried out under standard condition, like H2O is a gas, not liquid in this experiment. So what happened? Because according to standard condition, when we are working out or we are finding the enthalpy change, so if we are burning propanol, so prop means 3 carbon CH3, C3H7, OH propanol. When it burned in the presence of oxygen, a complete combustion gives carbon dioxide and water. So what happened? The state, the room temperature, this one is liquid, this one is gas, carbon dioxide gas, water is liquid. But practically, because when you're burning a substance, temperature is high, so this water, instead of produced as a liquid state, it might produce in a gaseous state. So water is produced in a gaseous state, then this water actually absorb energy which is released during a reaction. So you will not get the accurate answer, so enthalpy change value will be different. So these are some errors in this method which leads to wrong result. Is it clear? Now there is also another way to work out the enthalpy change during a chemical reaction. So what we can do, we can use a concept of the bond breaking and bond forming, as the bond breaking is endothermic, bond forming is exo. When we work out the difference between them, if bond breaking is more, the reaction will be endo. Bond forming is more, the reaction will be exo. So what are the bond energies? Basically the definition of the bond energy, or the mean bond energy first. The mean bond energy is enthalpy change needed to break the covalent bond into a gaseous atom, average over a different molecule. Like example, if we have methane, which is CH4, so how much energy is required to break these bonds and produce carbon and hydrogen atoms, but in a gaseous state? So when we produce a gaseous atom by breaking the bond, the energy required to break the bond, which is average over the different molecule. Example, here we are breaking 4 bonds. So if the energy release example is 600, or energy required is endothermic 600 kilojoule per mole or kilojoule. So what we will do, this is for 4 bonds. So if we need for 1 bond, so this should be divided by 4. So when we divide by 4, that will be equal to 150 kilojoule per mole. That will, this value 150 kilojoule per mole is known as the mean bond enthalpy, or of all the average energy required to break 1 bond within the structure to produce the atoms in a gaseous state. But practically, like we are getting this answer, the total energy required to break the 4 bonds, we are getting this 600. But practically what happened, the energy required to break, this is the total energy required to break all the four bonds. But practically, like, even the bonds are identical, but to break the first bond, example, we need 200. To break the second bond, we need 100. To break the third bond, we need 50, and so on. So what happened practically, even you're breaking the identical bond, but you need a different amount of energy because the stability of the atom, stability of the molecule decreases as the number of the bonds or bond break. So to break the first bond, we need relatively greater amount of energy. So mean bond enthalpy are not giving the accurate answer because this is the average value required to break the bond. And this definition is only applied for gaseous substance. Like we should have the substance in a gaseous state. As you can see, the mean bond energy is enthalpy needed to break the covalent bond into a gaseous atom. So we should have a gaseous atom to break the bonds. Now how we can work out this, the bond breaking energy and the bond forming, using a bond breaking and bond forming, how we work out the energy change. So for exothermic reaction, energy of the reactants is higher and energy of the product is lower. So minimum possible energy for us to start up the reaction, that's called activation energy. So when they reach the activation energy, they will react and form the product. So if I give an example, because during a reaction there is a bond breaking and there is a bond forming as well. So example, we have a reaction, we are burning methane and this result in a complete combustion, result in a formation of carbon dioxide in water. So the equation must be balanced, so we have this balance equation. Now as we know, the enthalpy change, this is a combustion reaction. Combustion reactions are exothermic. So when we make an energy profile diagram, the reactants have high energy and the product is having a low energy. And the minimum possible energy at which the reaction starts, that is called activation. So we have reactant first. So what are the reactant? We have methane and we have oxygen as a reactant, and the product which is formed, the carbon dioxide plus water molecule. So once they reach the activation energy, why they reach an activation energy? Because first the bond will break. So as the bond will break, so it is CH4, CH4 bond will break, so it will produce carbon in a gaseous state, it will produce 4 hydrogen atoms in a gaseous state, and it will produce 6 oxygen atoms in a gaseous state. That's a bond breaking energy. But when they start to react with each other, they will form the bond, that is a bond forming energy. So in this reaction you can, and they will form the final product. So in this reaction you can clearly see the bond breaking energy is less than bond forming. So if bond breaking energy is less than bond forming, the overall reaction will be exothermic. Because bond breaking required energy, it is taking in small amount and as a result it is giving out greater amount. The minimum possible energy for reaction to start to break all the bond, that energy is called activation energy. And the energy difference between the reactants and the product, that is called enthalpy change. This is for exothermic reaction. But same thing will be there for endothermic reactions. Like if you want to make for endothermic reactions, say thermal decomposition of calcium carbonate, So thermal decomposition of calcium carbonate CaCO3 result in a formation of calcium oxide plus carbon dioxide. So in endothermic reactions, reactants have low energy and the product is having a high energy. And what happened during this reaction, like you have a calcium carbonate and you have calcium oxide plus carbon dioxide. So the minimum possible energy required to start up this reaction, that's called activation energy. And so when we break the bond, so we should have according to bond energy, we should have a calcium in a gaseous state, we should have carbon in a gaseous state, and we should have oxygen in a gaseous state. So reactant will form, first break the bonds in the reactant, so bond breaking energy is there, and then bond forming. But bond breaking energy is higher, taken in more, and given out is less. So overall this reaction, because the bond breaking is more than bond forming, so the overall reaction will be endothermic. Is it clear? And the minimum, it's the same thing, the minimum possible energy to start up the reaction from reactant to the start of the reaction is activation, and the difference in the energy between the reactant and the product, that is called enthalpy change. So this one is enthalpy change and this one is the activation energy. So how we can work out using a bond energies, how we can work out the enthalpy change for a reaction. So in the question you will have reactant and product. If the bond energies are given, so what link you will add? You will add the gaseous atom. And what happened? The reactant might form the gaseous atom or the product might form those gaseous atom. And if we apply the Hess law here, so according to this law, the overall energy change is independent of the root. Where the two arrows are pointing out, that is the start of the cycle. And the position where the two arrows are pointing in, that is end of the cycle. So I can say delta, the enthalpy change of a reaction plus the bond energy of the product is equals to bond energy of reactant. Or if I need the enthalpy change, so it is bond breaking minus bond or bond energy required, because what we have, if I write, this is a bond energies broken in reactant and bond energies, the submission means the sum made in the product. So this is a bond forming, this one is bond breaking. So when we work out the delta H plus bond forming is equals to bond breaking, because this is root 1 for us and this one is root 2, or delta H is equals to bond breaking minus bond forming. But delta H value which is calculated using this method is less accurate. What is the reason why this method is not accurate? Because using a formation and combustion data, because the mean bond energies are not the exact. Like as I mentioned in the beginning, if we say the mean bond energy for CH bond is say minus 200 or 200 kilojoule per mole. Bond energy is because it's a bond break, endothermic reactions required to break the bond, so 200. But in practical it will not be 200 because that is the mean bond or average bond energy, and it depends on the neighboring molecules or neighboring atoms which are attached to carbon. So the mean bond energy may vary. Even like for example, you have a bond in methane, CH bond in methane, there are 4, and you also have CH bond in ethane. So even though the identical bonds are there, but they require a different amount of energy to break because the environment is different, the number of atoms surrounding them is different as well. So using a mean bond enthalpy, how we can work out the energy change. So it's bond breaking minus bond forming. As the structure is given, like a structure of propene reacted with oxygen gives complete combustion gives carbon dioxide and water. So bond breaking energy, what are the bonds we are breaking? We are breaking carbon-carbon bond, that's one only. Then we are breaking carbon-carbon double bond, that's another. Then we are breaking carbon and hydrogen bond. How many? 1, 2, 3, 4, 5, 6. So that's why it is multiplied by 6. And we are breaking oxygen-oxygen double bond, 4.5. So we'll get that energy. And for how many bonds? CO1 and 2 are there, but 3 molecules. So there will be 6 CO bonds and 1 and 2 OH bond, but 3 molecules, so 6 OH bonds. So bond breaking minus bond forming will get the energy change. If you are getting a negative answer, it means that this reaction will be an exothermic reaction. Is it clear, this example, how we use the bond energy, the mean bond energy values to work out the enthalpy change during a chemical reaction? You don't have to memorize these values, it will be given and you just, but these are not these are all mean bond enthalpies, but in practical the bond energies are different. So example, use the following mean bond enthalpy data to calculate the enthalpy change of formation of ammonia. So if we want the enthalpy change of formation of ammonia, in ammonia nitrogen react, the Haber's process, nitrogen react with hydrogen, which result in a formation of ammonia. When 1 mole of a compound is formed from its element, we call that as enthalpy change of formation. So N2 means nitrogen, nitrogen triple bond is there. And how many moles are there? Half mole. And hydrogen and ammonia. So bond breaking minus bond forming is equals to energy change. So 0.5 into nitrogen nitrogen triple bond, 1.5 into hydrogen hydrogen bond, and minus 3 times the NH bond, because one molecule you produce. So enthalpy change of formation for ammonia is negative 38 kilojoule per mole. So we can work out the enthalpy change of formation. How we can work out the enthalpy change of formation? The same idea, like elements are forming a compound, or what happen, elements might turn into gaseous atom or the compound might turn into gaseous atom. So the routes which we follow, elements form a compound, compound form the atom, is same as element directly form those atoms. So delta HF plus enthalpy change for gaseous atom of compound to turn gaseous atom of element. So basically when we take the difference, we'll get the enthalpy change of formation. That we did in example 9. Now in this question, enthalpy change of formation of propane C3H8 given the following data. So energy to convert the carbon solid into carbon gas, that is given 715. So what we can do, how we can work out this, like 3 carbon in a solid or 4 hydrogens are there, C3H8. So what we can do, we can have a carbon in a gaseous state we can have 4 hydrogen in a 8 hydrogen in a gaseous state. So this is the enthalpy change of formation. This one is a bond breaking and a bond for product, and bond energy for product, and this one is for bond energy for reactant. So enthalpy change to turn the element into gaseous minus enthalpy change to turn compound into gaseous is equals to enthalpy change of formation. So to convert the reactant, because when we make a cycle here, as we use the values, so here carbon in a solid state, we are converting carbon into a gaseous state. When we produce a gaseous atom, we call atomization. So atomization is given here, which is 715, but that should be multiplied by 3 because we are producing 3 atoms of carbon. That's why it's multiplied by 3. Plus, how many moles of the bond energy is given for hydrogen? So how many bonds are there in H2? There are 4 bonds with overall in each molecule 1, because there are 4 molecules, so 4 bonds will be there. So it will be 4 multiplied by 436. And for bonds in C3H8, so 3 carbon atoms are there and 8 hydrogen atom. So 2 carbon-carbon bonds are there and 8 CH bonds. So 2 carbon-carbon bonds and 8 CH bonds. So this is the bond forming energy, bond breaking energy. When we take a difference, we'll get the enthalpy change of formation for propane. Is it clear, this example? Then enthalpy change of combustion in homologous series, like when we have a homologous series, a series which is having a following characteristic: each member differ by CH2 and similar chemical properties, physical properties gradually change, same method of preparation, same functional group. So when comparing the heat of combustion of successive members of the homologous series, like alkane, alkene, there's a constant rise. As you can see, like here we have ethanol, then we are burning propanol and butanol. So for ethanol, it was 1365, then 2000, and then 2600. So what is the approximate, not exact, but approximate difference is about 700. Approximate difference is about the same, 700. So using this, we can just predict the value for enthalpy change of combustion. As a number of the bond increase, the enthalpy change will also increase. So we can predict the combustion of different members of homologous series. Practically, the practical values and the experimental values, like as you can see clearly in this one, when we go to the homologous series, there's a constant amount or type of extra bond is broken. So if the results are worked out experimentally using a calorimeter, the experiment results are much lower. Like using when we are finding the combustion using a calorimeter and we are calculating by this method, we are getting a higher value as compared to experimentally. Because what happened, there is an incomplete combustion. As there are more carbon atoms, we need greater amount of oxygen, and it increases the incomplete combustion of a hydrocarbon or a fuel such as alcohol. That's why the experimental values are always lower than the calculated value.